If you had to bet on who is the better learner, um, a billion parameter supercomputer or a 30-pound toddler who just learned to walk, who would you choose?
I mean, I think most people would instinctively put their money on the supercomputer.
Yeah,
Yeah.
exactly. Yeah. But the answer is actually going to surprise you. So, welcome to the deep dive. The mission today is to explore this ultimate learning showdown between large language models and human babies.
It is such a fascinating comparison.
It really is, because they are both, language learners, but their methods are just wildly different. We're unpacking a whole stack of cognitive science and AI research today to figure out what babies know that supercomputers just don't.
Right. And how those human toddlers might actually hold the blueprint for the next generation of artificial intelligence.
Which is crazy to think about. And I love this topic because, I get to marvel at human cognition and developmental psychology while you get to look at the actual system architecture on the AI side.
Yeah, and the contrast between the two is, well, it's striking because they represent fundamentally different architectures for, like, processing the universe.
Mm-hmm.
On the AI side, we're engineering these systems that simulate language with just breathtaking fluency. But the mechanical processes running those models, they have almost zero overlap with the neurobiology of a toddler acquiring their first words.
Okay, let's unpack this. Because to understand the difference between these two learners, we first have to look at what they actually consume, right? Like their data diet.
Exactly, yeah. You can't evaluate a learning system without looking at its diet.
Right. And the sources highlight this massive divergence here. LLMs operate on a diet of text that is, it's almost incomprehensible in scale. We're talking about billions or even trillions of tokens.
Yeah, they are incredibly data hungry. And we should probably define what a token actually is in this context because it really dictates the whole architecture.
Yeah, go for it. Because it's not just a word, right?
Right? A token isn't necessarily a whole word. It's often just a fragment of a word or even a single character.
Okay.
So when an LLM ingests those trillions of tokens during its pre-training phase, it isn't reading them like you or I would read a book.
Right, it's doing something totally different.
Exactly. It's mapping them into this incredibly high-dimensional mathematical space. So every concept gets turned into a vector.
And a vector is basically just a set of coordinates.
Precisely. It's a set of coordinates. The model determines meaning purely by calculating the statistical distance between those coordinates.
Oh, wow. So it's all just math.
Yeah, it's all math. So the vector for the word apple ends up positioned mathematically close to the vectors for red or, orchard.
But the wild thing to me is that the model is doing this in a complete vacuum.
Yeah, exactly.
Like I was thinking about this analogy earlier. LLMs are basically like someone trying to learn a language by being locked in a dark room and just forced to read the entire internet.
That is actually a really perfect way to describe it.
Right. It's just a randomized, completely disembodied stream of text.
And it has to be fed that much data because it is entirely reliant on passive pattern matching.
Passive being the key word there.
Exactly. Modern AI relies on this mechanism called self-attention. Because the machine has no physical context to understand what a word actually means in the real world, it has to look at every single word in a document.
Just to figure out the context.
Right. It calculates how strongly it relates to every other word. And to build a reliable statistical map of all those relationships, the system requires a violently data-hungry approach.
Violently data hungry, yeah. Which is where those scaling laws come in, right?
Exactly. Scaling laws are basically the mathematical rule in AI that says if you simply throw more compute power and more text at the network, its error rate drops.
But then you look at developmental psychology, and the research shows human cognition just rejects that scaling law entirely.
Yeah, it's a completely different paradigm.
Right, because a human baby achieves fluency on a tiny, almost infinitesimal fraction of that data. Babies get a personalized interactive tutor instead of a dark room.
Which makes them incredibly data efficient.
Exactly. If an LLM is a machine trying to map relationships between trillions of abstract coordinates in a void, a baby is this biological network processing highly curated, incredibly dense signals.
And the AI field studies that efficiency really closely. because we build models that require the whole internet just to learn basic grammar.
Right, while a toddler figures it out from just a few thousand hours of
It's
interaction.
humbling, honestly.
It really is. And the mechanism behind that human efficiency is what psychologists call joint attention.
Right, which is so crucial.
It's huge. A baby isn't just passively absorbing background noise like an AI does. A caregiver acts as a dynamic, real-time filter for the child's data diet.
They're curating the input.
Exactly. Like when a parent teaches the word cup, they don't read out a dictionary definition. They track the baby's gaze. They see the baby actually looking at the physical object.
Right, they ground it in reality.
Yeah, they exaggerate their tone, they point at it, and they say the word cup at the exact moment. The baby's neural pathways are primed for that specific sensory input. The caregiver is actively reducing the noise in the data stream.
Which is really just an externalized version of the attention mechanism we try to program into neural networks.
Oh, wait, really? How so?
Well, AI uses matrix multiplication to weigh the importance of text tokens,
Mm.
but the human infant uses the caregiver's social cues to weigh the importance of sensory input.
Oh, that makes so much sense.
Yeah, but the fundamental difference is that the AI's data is purely linguistic, whereas the baby's data is grounded in the physical space.
Right. And here's where it gets really interesting, though, because I actually want to push back on this assumption a little bit.
Okay, let's hear.
Like, is physical grounding really the ultimate trump card? Because if you sit down at your laptop right now and prompt an LLM to write a poem about, say, sitting by a campfire,
Right.
and it outputs this beautifully evocative description of the crackle of the wood, the smell of the smoke, the warmth on your face, does it actually matter to you and me that the computer can't physically feel the heat?
That's a fair point.
Like, from a practical standpoint, if the output is completely indistinguishable from human writing, why do we care that the AI lacks a physical body?
Well, what's fascinating here is the distinction between merely simulating a phenomenon
Uh-huh.
and actually possessing a causal world model.
Okay, causal world model. Break that down.
So when the LLM generates that beautiful campfire poem,
Mm-hmm.
it's executing an immensely complex probabilistic calculation.
It's just predicting the next word.
Exactly. It predicts that the token warmth has a really high probability of following the token's campfire and face based on that vector mapping we talked about earlier.
Right.
It is an incredibly convincing simulation of comprehension, but it completely lacks an underlying physics engine.
Meaning it knows the statistical shape of the language, but it has absolutely no internal constraints based on physical reality.
Exactly the problem. And because an LLM operates entirely in that abstract token space, it will routinely fail at really basic physical reasoning tasks.
Tasks that rely on unstated real-world rules, right?
Right. Like the sources give a great example. You can prompt an advanced LLM with a scenario where someone balances a heavy iron anvil on top of a fragile raw egg.
Oh, yeah, the anvil and egg test.
Yeah. The model might write a perfectly grammatical, structurally sound paragraph about the anvil resting safely on the egg.
Completely missing the fact that the egg would just instantly shatter.
Exactly. Because it doesn't have a sensorimotor understanding of heavy or fragile. It only has statistical correlations.
And a baby's brain prevents that kind of hallucination because its language centers are actually physically wired to its sensorimotor cortex.
Right. It has embodiment.
Yeah. When a baby learns the word cup, they aren't just filing away the letters CUP in an abstract database. They are physically wrapping their fingers around the plastic.
They're feeling it.
They're feeling the weight of the water inside it. If they tip it too far, they experience the actual shock of cold water spilling on their chest.
Which is a very strong learning signal.
Yeah, definitely. The neurobiology of learning a word involves multimodal integration. The auditory signal of the word is permanently mapped to the tactile sensation, the visual shape, and the motor plan required to interact with it.
The word is completely anchored in the physical reality of their nervous system. And that embodiment, that's exactly what AI researchers are currently agonizing over.
Really? They're trying to solve that.
Oh, absolutely. We've engineered software that is unparalleled at producing fluent text. But because it's completely untethered from physical reality, it cannot intuitively grasp the physical constraints of the universe.
Which naturally brings us to a massive divergence in their actual operational style.
Right. How they actually go about learning.
Because you cannot build that physical intuition just by passively observing data. To truly map the constraints of reality, you have to actively mess with it.
You have to intervene.
Yes, active intervention. As someone who loves the developmental psychology side of this, I can tell you that babies are the furthest thing from passive receivers.
Oh, they're pure chaos.
Exactly. They are basically tiny, chaotic scientists running nonstop physical experiments.
And the scientific term for that, by the way, is active inference.
Active inference, I like that.
Yeah, they're continuously testing hypotheses against their environment.
Like, when a toddler sits in a high chair and deliberately pushes a bowl of peas off the tray, they aren't just making a mess to annoy you.
Oh, it does annoy you.
Right, it does. But cognitively, they are isolating a variable. They are testing gravity.
Right.
And then they drop a spoon to see if it makes a different sound. Then they pour their milk out to see how liquids behave compared to solids.
They're building a data set of physical reactions.
Yes. They are poking, biting, pulling, and manipulating their environment just to see what happens. And when they finally acquire enough language, that physical probing evolves into this endless loop of asking why.
Oh, the why phase.
The famous why phase. But they are actively interrogating the universe to build out that internal physics engine we talked about.
And this is where the comparison gets really stark, because the architecture of a large language model fundamentally prohibits that kind of active intervention.
Because they're stuck in the dark room.
Right. LLMs are passive correlational engines. They are static observers just waiting for a prompt.
Wow.
An LLM cannot wake up, realize it has a gap in its knowledge regarding, say, fluid dynamics, and deliberately decide to seek out novel data to resolve that confusion.
Because it only knows how to process the static data set it was already fed.
Exactly. It can't drop the spoon to see what happens.
It can only read a million descriptions of other people dropping spoons.
And that reliance on observation over intervention, that is a critical bottleneck in computer science right now.
How so?
Well, in the field of causal inference, there's this concept called the ladder of causation.
Okay.
The lowest rung on that ladder is mere observation. Just seeing the two things happen at the same time and associating them.
Like pattern matching.
Exactly. And that is exactly where LLMs live. So imagine you observe a rooster crowing every morning right before the sun rises.
Okay.
If you only observe, you might statistically correlate the rooster's crow with the sun coming up.
Right, you would just assume the rooster actually causes the sunrise.
Exactly. But to understand that the rooster does not cause the sunrise, you have to move to the next rung on the causal ladder, which is intervention.
Ah, active intervention.
Right. You have to actively go out, gag the rooster, and then wait to see if the sun still rises anyway.
Yes, it does.
Right. And because babies are active agents who constantly intervene in their environment, they can intuitively test the rooster.
They isolate the variables.
Exactly. They isolate variables, which allows them to generalize causal rules from just a handful of examples. A baby drops a heavy block and sees it fall. They immediately understand a toy car is also going to fall.
That is so efficient. While the AI needs to ingest like millions of parameters of falling objects just to build a mathematical proxy for gravity.
Yeah. The toddler achieves comprehension through agency, while the supercomputer simulates it through brute force statistics.
So what does this all mean? Like, for the actual development of future technology, we've established that humans learn deeper, faster, and more causally than current AI.
Right.
But how do we actually translate the neurobiology of a toddler into system architecture? Because this feels like a major limitation for AI.
It is a major limitation, and it's forcing a massive reckoning in the artificial intelligence community right now. It points toward a real paradigm shift in how we design artificial general intelligence, or AGI.
Right, AGI. So are we talking about fundamentally changing how we build these models?
If we connect this to the bigger picture, yes. Many cognitive scientists and machine learning engineers are arguing that those scaling laws we discussed, they're hitting diminishing returns.
Like throwing more text at it isn't fixing the core issue.
Exactly. We can't just keep adding billions more tokens and expect the models to suddenly magically develop causal reasoning.
It's still just observation.
Exactly. If we want future AGI to stop hallucinating bizarre physical impossibilities like the anvil on the egg and actually understand the world, we have to move away from static, text-based pre-training.
Okay, so what's the alternative?
We have to build systems that learn more like biological organisms.
Wait, the implication there sounds wild. Are researchers suggesting we have to actually put AI brains into robotic toddler bodies so they can stumble around a playroom knocking over blocks?
I mean, embodied AI in robotics is certainly a major frontier right now.
Really?
Oh, yeah. By giving a neural network a physical actuator, like a robotic arm, and letting it feel resistance, weight, and spatial geometry, it actually begins to ground its language tokens in real sensor motor feedback.
That's incredible.
But the paradigm shift isn't just about building physical robots. It's about fundamentally altering the training environment itself.
Right, because even a digital environment can be structured, right? Like, we don't necessarily need metal and plastic.
Yeah.
In human development, we rely incredibly heavily on scaffolding. A baby's environment is highly structured by their caregivers and, honestly, by their own biological limitations.
Yeah, they don't learn everything at once.
Right. A baby doesn't try to parse complex grammar before it understands basic object permanence. It learns the physical rules of the room first, then basic nouns, then verbs, then syntax. It happens in stages.
And you are describing exactly what AI researchers call curriculum learning.
Curriculum learning. Okay.
Yeah. The field is realizing that dumping the entire ocean of human knowledge into a model all at once is just wildly inefficient.
Like the dark room again.
Exactly. Instead, we need to create staged, simulated developmental environments for digital agents.
Staged learning for an algorithm. That's fascinating.
Precisely. So first, you drop the AI agent into a simulated physics engine. You force it to learn basic spatial navigation and object permanence through trial and error.
Right, through reinforcement learning.
Yes. You force it to learn the consequences of its actions. And then, once it masters the physical rules of its simulated room, you introduce basic language tokens that map to those objects.
And you slowly increase the complexity of the environment, just like a child's cognitive capabilities expand over time.
Exactly. You introduce agency, you design an architecture where the system updates its internal weights, not just by passively reading text, but by making a prediction, taking an action in an environment, and experiencing the consequence of that action.
Wow.
Uh.
You are basically designing a digital childhood.
Yeah.
You are giving the algorithm a chance to be curious.
Yeah, that's a great way to put it. It's moving the whole field of AI from purely predictive text generation to building actual causal models of reality.
It radically changes how you view intelligence, doesn't it?
It really does.
We spend so much time analyzing the sheer processing power of these massive server farms, but the most advanced, causally aware learning algorithm we know of operates on like 20 watts of energy. And it is currently sitting in a high chair somewhere, dropping a toy on the floor for the 50th time just to see what happens.
It completely forces us to respect the brilliance of biological evolution.
It really does. So to bring all of this together for you listening, large language models achieve their incredible fluency by scaling massive amounts of abstract data to calculate statistical probabilities.
But human intelligence scales through highly curated, deeply physical experiences.
Exactly. We use agency and embodiment to truly map the universe.
And I think the core takeaway for anyone interacting with generative AI today is just to recognize it for what it actually is.
Yeah.
It is a marvel of mathematical engineering and pattern recognition, truly. But it is not a causal reasoning engine.
Yeah.
The toddler beats the bot when it comes to true comprehension because the toddler is actually participating in reality rather than just reading about it in a dark room.
That is perfectly said. And that leads to a final thought I want to leave you with, building entirely on this idea of curiosity and active inference. If the future of robust artificial general intelligence requires training these systems to be active agents, if we have to design algorithms that deliberately seek out surprises, intervene in their environments, and constantly ask why to probe cause and effect,
Right.
what happens to our relationship with technology when our computers stop just passively answering our prompts and start asking us why we gave them those instructions in the first place?
Oh, wow. That is a wild thought.
Think about that. We will see you on the next Deep Dive.